Okay, while you're finding your waves notes there, quick reminder, the last thing that you are going to hand in to me, the simple harmonic motion assignment, is due tomorrow. Okay, so make sure you get that done. I will not be assigning anything else to come in, okay, for the rest of the semester. You will just have your Unit 4 exam and your final exam left. Okay, also a reminder, this, okay, and that is that if you have any overdue assignments and you would like to have them added to your grade, I need to have them by June 15th at 3:20 so that I can put them in there. Okay. All right, for today, we are going to start waves by looking at the properties of waves. What is a wave? How does a wave travel? What does a wave need? What are, okay, yeah, so lots of things that we'll talk about to do with waves today and obviously for the rest of the unit. All right, so the first thing we got to look at are the two types of waves. You may not have known this, but there are actually two types of waves. There are transverse waves. Those would be things like water waves like you'd see on the ocean. Okay, and there are longitudinal waves, and yes, that is spelled correctly. Okay, longitudinal are lines on a map. Okay, longitudinal are waves whose displacement and direction of travel are parallel. Two different things. Okay, all right, sound waves are longitudinal waves, right? Whereas, like I said, water waves are transverse waves. Light is a transverse wave, and a particle. It's weird. Okay. Earthquake waves, there's both kinds. And there's all kinds of earthquake waves, and they can be of both types, longitudinal and transverse. Okay, so we'll be looking at those and kind of how they look and how they travel. Okay, understand how waves are created and propagated, and understand the properties of waves. All right, so what is a wave?
Movement of energy.
Okay, a wave actually kind of is energy. Okay, a wave actually isn't matter. And that's kind of the weird thing about it. It needs matter to travel, to propagate, but it isn't matter in and of itself. It is a traveling disturbance. I mean, think about how you make a wave. Okay, like right now I'm making waves. My vocal cords are vibrating back and forth, and they're disturbing the air around them, and that disturbance travels towards you, and you have to listen to it. Okay, so it's a traveling disturbance. Okay, I'm using energy to create a disturbance in the air. And if you throw a rock into the water, the waves travel outwards from it because the energy of the rock disturbs the water, pushes the water down. I don't know if you've ever seen a splash in slow motion, okay? But the water is very elastic. It looks like a rebounding effect. That's why you get more than one wave. Okay? So the rock penetrates the water, disturbs the water downwards, the water comes back up, and it oscillates up and down with simple harmonic motion for a short period of time, creating multiple waves from only one rock. Okay? But it's still a disturbance of the water, and that disturbance travels away, carrying the energy with it. How do we know waves carry energy, or are energy? What can they do?
Do work.
They can do work. Okay, we know that. Tidal waves are very destructive, or if you're surfing, okay, you're using the energy of the wave, you're traveling on it. Right? So they carry energy because they can do work. Okay, so a wave, like we said, is a traveling disturbance, and a wave requires a medium, with the exception of light, okay, in which to travel. That could be water, it could be air, it could be wood, it could be steel, okay, as long as there's something that can oscillate, okay, some matter that can bounce back and forth or whatever. All right, so can sound travel in space? No. Okay, it's an old line from the first Alien movie. In space, no one can hear you scream. It's true. Okay, sound won't travel in space. Now, granted, if you opened up your visor and screamed into space, the fact that no one could hear the scream would be the least of your worries, because you'd explosively decompress. That would be a big problem. Okay, but it wouldn't work. In fact, if an astronaut's radio dies, okay, in order to communicate with someone else, they have to put their visors together, so that the sound will travel in the air inside the one person's suit to the glass and travel through the glass and into the air in the other person's suit. It's the only way to transfer the waves. It's very similar to, you guys probably didn't do this because you had cell phones when you were kids, but you ever make the tin can phone with the strings? Okay, that's what we did. Okay. The same idea is true. You talk into the can, and the bottom of the can takes the waves that you're producing and it vibrates, and that vibration is conducted along the string to the other can. As long as the string is tight, this works. okay, and the other can receives the vibration and it vibrates, and then you hear it. Okay, so it's the same idea. If I speak, okay, the air inside my helmet vibrates, it makes the glass of my visor vibrate, and if that is in contact with someone else's visor, it'll travel through it. Okay, but that would be the only way. Okay, so gotta have a medium in which to travel. If there's no medium, it won't. Again, light is the exception to that because of the wave-particle duality of light, which you learn more about in Physics 30. Wave is both, or light is both a wave and a particle, so it's its own medium. Strange but true. Okay, now here's the other thing. People get this one wrong too. A wave is not a bulk movement of water like a river. Okay, when a water wave travels through the water doesn't go with it. Okay, we get this idea because of tidal waves and because we've sat on the shore of the ocean and watched the water come in, or so we think. Okay, it seems like the water is moving. Well, the water's not moving from forward and backward. The water is moving up and down. Okay, so as the wave travels through the water, it displaces or disturbs it up. Okay, and then back down, and then back to equilibrium, just like simple harmonic motion. That's what a wave is doing, is making the water oscillate. Okay, now we all see these, pictures and videos of tidal waves coming in, and okay, we see the ocean come in and inundate these coastal cities. Well, what's really going on there is not that the wave has moved the water in and that the water has gone in. The wave has disturbed the water upwards, and then it's left. It's gone from being in the water to being in the air. Okay? And in fact, when a tidal wave comes in, just before it crashes, you can actually feel a little gust of wind because the wave has actually traveled into the air. Okay? And then suddenly, the energy that was holding up this column of water is gone. So now what does the water do? It just falls back down and splashes in. It's actually the splash that causes all the damage. Okay? The water gets disturbed upwards and then comes back down. Now, we see tidal waves. I'll show you some videos here, but we see tidal waves on the news and things like that. Okay? It just looks like it's just coming in and you can't control it. But out in the deep water, a tidal wave isn't very big. Okay? If they're caused by earthquakes, and the earthquakes are only going to move the earth a little bit. Okay? So a tidal wave out in the deep water, if you were on a boat, okay, the tidal wave would pass under your boat and you'd go like, you might go up a meter, 2 meters maybe. Okay, I mean, on a boat that'd be a bit of a ride, but if you're on a cruise ship, it'd be like, meh, hardly even notice it, right? But as it gets closer to shore, what happens to the depth of the water? It gets shallower. Now, here's the thing about waves. The depth of the water is a property of the water, okay? And the properties of the medium the wave is traveling in influence its speed. So as the depth of the water decreases, so does the speed of the wave. Now here's the problem with that. The front of the wave slows down before the back of the wave. Tidal waves in deep water can be very long. And so the front of the wave slows down and the back of the wave catches up and squeezes the wave. Where's the only way it can go? Up. Okay? That's why all waves get bigger closer to the shore. They're slowing down. Their wavelength is getting shorter, and their amplitude, because energy has to be conserved, has to get bigger. Okay? Because the measures of energy for the wave are kinetic energy, its speed, okay? And amplitude, kind of its potential energy, okay? Its height. So since energy has to be conserved, if I reduce the kinetic energy of the wave by changing its speed, the energy goes into potential and gets really, really tall, right? And then when the water runs out, it falls back down, and all that potential energy turns into destruction, okay, as the tidal wave comes in. All right? Everybody with me there? Now when you're thinking about that, sitting on the beach and seeing the water come in, right? It goes in and out, in and out, in and out. Okay? If a wave was a bulk movement of water, eventually all of the ocean would be where? In the land, and there'd be a big hole in the middle of the ocean. Okay? Because all the water would go this way. It doesn't go that way. It just oscillates up and down. Okay? And that's why we see the waves kind of do this. And every once in a while you get a big one. Okay? And that's actually an interference thing. When the waves get to the shore, they actually reflect off the shore and they go back out. And when they meet up with an incoming wave, they meet up just right, they get taller. And then that's why every once in a while you just time it right, and one of the waves gets a little bit bigger and the water comes in a little bit further and wrecks your sandcastle. Okay, kind of like that. Okay, so a wave carries energy from place to place. We know that because if this motorboat goes by this guy in the fishing boat, okay, his fishing boat is going to go up and down, up and down. Does it take energy to lift the boat? It does, okay, that's the wave. It's traveling through the medium, it's carrying the energy. That energy can do work by lifting up the boat. Okay, everybody all right with that? Okay. All right, I just gotta grab the slinky here. Okay, the wave is gonna travel from me towards Emma, right? But the spring, the slinky, is gonna go out and back, okay? Those two motions are perpendicular at 90-degree angles to each other. So I'm going to disturb the spring out to my right. Okay? The wave traveled perpendicular to the direction I disturbed the spring. Okay. Now when it hits Emma, it reflects off of her, okay, and it comes back. The reflection is actually the other way. We'll talk about that later in the unit. Okay? But that's a transverse wave. Okay? The disturbance and the direction of travel are at right angles. The other kind of wave is longitudinal. In a longitudinal wave, the disturbance and the direction of travel are parallel. So a longitudinal wave looks like this. I'm disturbing the medium forward and backward, okay? And it's traveling parallel to the disturbance, okay? Everybody all right with that? So those are the two kinds of waves, okay? Pretty easy to remember? Okay, thanks, Emma, you can let it go. Okay, so you can see here, this is the transverse wave, okay? And just as I did with the slinky, it's disturbed up, okay? And then the wave travels to the right, so perpendicular or transverse. And you can see here that the oscillation, if I was to continue to make waves, the oscillation is up and down, but the direction of travel is left to right. Okay. And then this is the longitude, oh, sorry. So a transverse wave is one in which the disturbance is perpendicular. Now, terminology here, not new, but applied to waves. The maximum displacement of the medium in which the wave is traveling from its equilibrium position is still called the amplitude, okay? Just as it was in simple harmonic motion. Okay? The upward part of a wave is called the crest. The downward part of the wave is called the trough. Okay? And then obviously we have the equilibrium position. And the distance from one point on a wave to its next equal point is one wavelength. Okay? Because that's the length of one complete cycle of the wave. So I'm just going to show you here that any two equal points on a wave are exactly that far apart. Okay, so the red line is one wavelength. Okay, so those 2 points are one wavelength apart, as are any two equal successive points on a wave, including equilibrium positions. Why is this equilibrium position not considered equal to those two? Which way is the medium going at this equilibrium position? Which way is the medium going on this one? Down. But this one is one full wavelength from the other down part of the wave. Okay, so any two equal successive points on a wave are one wavelength apart. So two crests, they're one wavelength apart. Two troughs, they're one wavelength apart. Two equal equilibrium positions, one wavelength apart. Everybody okay with that? So one length of one cycle is the wavelength. What do we call the amount of time it takes for that cycle to happen? Period. How many cycles per second is? Frequency. So all those terms still apply to waves because they're an example of oscillatory motion. Okay, now got a couple of videos to show you here. What's some of the stuff we're going to look at is going to be like. Okay, so those are all transverse waves, okay, because they go up but travel forwards. Okay? The other type, as we said, are longitudinal waves. Again, I demonstrated those with the slinky by moving it back and forth. Sound waves are longitudinal waves. So if you've ever watched, like, if somebody has a subwoofer, okay, and in their car or something like that, you can actually see a subwoofer move back and forth because it moves at a low enough frequency that we can actually visualize it. Okay? So as that speaker moves in and out, it's compressing the air and then stretching it. Okay? It's creating what we call a compression and a rarefaction. Those are the two parts of a longitudinal wave. Rather than a crest and a trough, okay, it's a compression and a rarefaction. That's why you can feel sound. You feel the compressed air hitting, okay, your eardrum, or you're in a car with subs, you can feel it hitting the back of your seat. Okay? That's the force of those waves coming in. All right, so compressions and rarefactions are part of longitudinal waves. All right, so the oscillation is back and forth, but the direction the wave travels is parallel to that. Okay, so in a longitudinal wave, alternating disturbances of compression travel parallel to the direction of the wave. So you can see that kind of in freeze frame right here. That would be a compression. This would be a rarefaction, okay, where it's stretched out.
What about square waves? Because isn't there like square waves that happen?
Oh, yeah, I think I've seen those. Again, there's still a type of, there's more to do with reflection. There's something under the surface that's causing that formation to occur. Okay, and on this one here, they marked one particular link in the slinky, okay, or ring in the slinky, and it goes out, okay, and then it'll come back, right, and it'll keep oscillating back and forth. Okay, so you can see it started at equilibrium, okay, that would be right here, and then it moved out, okay, and then it moved back. So that same link on the slinky is just oscillating back and forth. All right, so transverse and longitudinal waves are examples of periodic waves. That means they have a period and a frequency. They're the result of an oscillation of simple harmonic motion, okay, and which is why simple harmonic motion can make sinusoidal wave patterns. Okay? So as we already said, terminology-wise, the length of one cycle is called the wavelength. And this little symbol here is the symbol we use to denote wavelength. It is the Greek letter L, or lambda. Okay? It is a long stick supported by a short stick. Okay? You don't have to actually, it actually looks like this. It's like that, but nobody ever draws it with the curved end. We just like that because it's faster. Okay, so that's lambda, it's the Greek letter L, and stands for wavelength, because obviously L already stands for length, so we need something else for wavelength, so that'll be it. Okay, amplitude, again, you got an amplitude that's up or down, or in a longitudinal wave, forward or backward. Okay, so just make sure you're aware for those terminologies, because they still apply here. Okay. Like I said, amplitude, still the maximum excursion of a particle of the medium from that particle's undisturbed position. Okay, it is a measure of the energy of the wave as well. Okay, and yeah, so distance between crest and equilibrium, or trough and equilibrium, okay, for both of those. Okay. All right, wavelength, we already talked about that. So that's what lambda actually looks like, because I can't draw. But, you don't have to draw it as fancy as that, just long stick, short stick. Okay, that's lambda, that'll do. Okay. And remember, the wavelength is the distance between any two successive equal points on the wave. So two troughs, two crests, two equilibrium positions both going up, two equilibrium positions both going down, or any two other equal points. Okay, time for one cycle is still called the period. The number of cycles per second is still called the frequency. Okay, all of that stuff still applies here for properties of waves. Okay, so properties of waves. We got wavelength, we got speed. Okay, we've got period and frequency and all that kind of stuff. A good analogy of that is kind of like a train. Okay, so if the train is moving, it's moving at a certain speed. So the speed of the train is the speed of the waves. Each car is like one single wave. Okay? The amount of time it takes one car to go by is the period. Okay? The number of cars that go by every second is the frequency. Okay? Things like that. Everybody okay with that? Now, here's something you need to know that's super important about waves. Frequency and period of a wave never, and this is one of those weird things, it is absolutely an absolute, never change. Once a wave is produced, its frequency is fixed. Okay, its frequency cannot change once it is produced, because the frequency is caused by the source, okay, or determined by the source. Now, if a wave slows down, so its speed changes, what happens to its wavelength? It gets shorter. So, when a wave slows down, the wave gets shorter, which is why the frequency won't change. The wave is now going slower, but it's also shorter, which means now all the waves are closer together. Okay, so the same number of waves is still going to pass you every second as the observer because they're traveling slower and they're shorter. Okay, same happens if it speeds up. If a wave speeds up, it'll get longer. So now they're traveling faster, but they're longer, and the same number of waves will still pass you every second. The frequency of a wave can never change once it is produced. Okay, so it works kind of like this. Out here, just by the stoplights, for whatever reason, the speed, well, now the town's expanded out far enough that there's probably a reason for it, but there didn't used to be. The speed limit would change from 100 to 60. Okay? Now, if I'm standing out where the speed limit is 100, so let's just draw it out here. Let's say that this here line is where it goes from 100 to 60. Okay? Out here on the road, the cars are traveling 100 kilometers an hour. Okay? And I'm standing there and I'm counting the number of cars that go by every second. And let's say it's 2 cars per second. Now, when this car hits the speed limit change, what does it do? Assuming the person's following the rules. It slows down. What about this car? It's still going 100. It's not here yet. Okay? So imagine that these are waves. This wave hit the slow stuff first. It slows down. This wave isn't there yet, so it catches up. Okay? A little while later, here in the 60, this is what I see. Those same 3 cars are now a lot closer together. But 2 cars go by me every second. That part hasn't changed. They're going slower, but they're closer together. So the frequency doesn't change. Everybody with me there? Okay, so, I mean, you guys have taken your driver's ed probably. Okay, following distance, right? You got to follow. You got to make that bigger when you're going faster. Okay, when you're going slower, it's going to be a shorter distance. Okay, well, it works as a good analogy for waves. The frequency of the waves isn't going to change. Okay, even if their speed changes, because when their speed changes, their wavelength will change. Okay, and so will their amplitude. Okay, a longer wave is probably going to have a shorter amplitude. A shorter wave is probably going to have a higher amplitude. Okay, again, it's about conservation of energy. Okay, so waves are an example of simple harmonic motion because they repeat over and over, or more accurately, they're caused by something that is oscillating and repeating over and over again. Okay, so mass on the spring makes a sinusoidal wave pattern, okay, as it goes along, as it oscillates. Okay, well, we've done a little bit early. Okay, so that's all we had to do for properties of waves. Tomorrow we're going to move on to universal wave equation, which has to do with that car example I just told you about with the frequency never changing. So, you got a few minutes left here. Maybe you can work on your simple harmonic motion side if you're not done. Okay, and get that finished. Okay, I am going to post your final exam review